Hey Tanya,
Hello.
how are you?
I'm good. How are you doing?
Doing good too. Um, the IR quiz, you said you only missed one question. It was with SP3 peak when it would ask you if it was sharp, broad, or complex.
Oh, it was sharp. I
It was
got,
sharp.
I mean, it was complex. Sorry. I
It
put
was
complex,
complex. Oh, so you got it right.
but I did miss one point on a true or false question. It was silly. If I reread it, I would have changed my answer.
Yeah. Do you remember what it was?
Yeah, it was like, can you like guess the actual molecule? And I was looking at a practice and it says compared to the unknown. So I was thinking about that and I
Mm.
put true.
Hmm.
But it didn't mention comparing to an unknown. So
Mm.
yeah,
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 yeah, true. It is a comparing to unknown.
yeah.
Dang, that's good. But you got everything else correct. That's pretty
Yeah,
good. That's
yeah.
pretty
I think this is
good.
my highest discussion.
Yes, IR stuff, huh?
Yeah.
Hmm. Now you're learning about H&MR?
Yeah.
Yeah, okay. So, is this the most recent quiz that you had on H&MR?
No, that's just like one I got from one of my friends.
Oh yeah. Like, do you have the key for this as well?
Yeah, I do.
Uh-huh. Okay, okay, that's good. We
Yeah,
can
some of them are wrong.
some of them are wrong, yeah. We can go over this. So let me just show you what I like to think about when I think of H&MR,
Okay.
right? So, to review IR, they show you the functional groups present. Right. On the unknown molecule, but for H&MR, it's more specific in that it tells you the specific hydrogens in the molecule and where they are located at. Right? Like H&MR is very powerful because it tells you what your unknown molecule will look like. Right? And there's like three things I look at when I look at H&MR. I look at how de-shielded the peak is, and then I'll go over what this means later, but these are the three things I look for when I think about HNMR. De-shielded the peaks are, the n+1 rule, or the number of neighbors, right? And it'll make more sense as we'll go over an example, but let's go over the concept stuff so we could go over the vocabulary. And after we go over the vocabulary, we can do a practice problem on that. And then after that, I look at the integration, right? So let's say, for example, we have an unknown molecule, and we shine spectroscopy through it for 18MR. The graph is going to go from 0 to 12, right? Where like 0 is going to be at the right side, and then 12 is going to be at the left side. And then going up to the right, like anything to the right, is going to be called the shielded region. And then anything going to the left is going to be the de-shielded region, more de-shielded region, right? Okay. So what that means is that um, when we have a hydrogen of the molecule going through, if that hydrogen is bonded to a non-electronegative atom, like let's say carbon, for example, that hydrogen is going to be surrounded by electrons, like that, normally, right? So when we shine HNMR light through it, um, this hydrogen here will be shielded by electrons. So this HNMR here cannot pick up that hydrogen. It cannot read that hydrogen very clearly because it's um, being shielded by electrons, right? So, for example, if the hydrogen is bonded to an electronegative atom or electron withdrawing group, where the group withdraws electrons, the hydrogen's electrons will be shifted towards the electron withdrawing group or electronegative atom. And this right here would be de-shielded, right? Because this hydrogen is de-shielded by electrons, whereas this hydrogen here will be shielded by electrons. Okay. So there's gonna be different regions that you look for when you think of HNMR. The first thing that I like to see is gonna be like the shielded region is gonna be more complex to think about. The shielded region I mean the shielded region is more complex. The de-shielded region is more clear, right? So 0 to let's say 2 is gonna be the regular alkane region, right? Where um the hydrogen here is gonna be bonded to carbons that are not next to any other groups, right? Um 2 to let's say actually let's say 3. They say 0 to 3 is that region. 3 to oh wait, no. 0 to 2. 0 to 2, yeah. 0 to 2. 2 to 3. 2 to 3 is gonna be the alpha region. Where the hydrogen is gonna come off of an alpha carbon, um, of a pi bond. Right? So what that means is that the hydrogen in this region is gonna be coming off of the alpha carbon next to a pi bond. So this carbon here has a pi bond, right? Because it's sp2 hybridized. The first carbon away from that pi bond is the alpha carbon. So this hydrogen here is coming off of the alpha carbon, so this is an alpha hydrogen. Another example that you could have is this right here, where we see that,
I think this
uh-huh.
is for next week.
Oh,
Like
this is for next week right here.
yeah. NMR part one, it was more on just vocab and
Mhm.
then chemical equivalents and then chemical shifts.
Oh, chemical equivalents and chemical shifts, like how many peaks you would expect in HNMR, unique peaks, right?
Yeah.
Yeah,
Yeah.
yeah. Okay, so let's go over that first. And then we'll go over this next week right here. So let's say, for example, we have this molecule over here, and then we put that molecule through HNMR, right? So what HNMR will read is the unique sets of hydrogens, right? What that means is that um, there's gonna be multiple hydrogens in this molecule, right? So there's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens total in this molecule. And then there's gonna be sets of these hydrogens that are gonna be the same, right? So you know how all of these are single bonds right here?
Yeah.
These single bonds or sigma bonds can do free rotation. So let's focus on this sigma bond right here or single bond. We could do free rotation like that. And when we do that, these 3 hydrogens right here are gonna rotate into each other's spots like that. So we're gonna call these 3 hydrogens chemically equivalent. Like they have the same chemical environment, right? This hydrogen here is chemically equivalent, like it's its own unique hydrogen because there's no other hydrogens like it, right? This right here is gonna be um its own set of hydrogens, and then this set right here is gonna be its own set of hydrogens, right? Because these 3 hydrogens here have the same chemical environment. Like if we were to rotate this bond right here, the single bond right here, keeping everything on the left side the same, and rotate these 3 groups around, they're gonna experience the same environment, right? So in total, there's gonna be 1, 2, 3, 4 unique sets of hydrogens in this HNMR. Any questions on that, Tanya?
Yeah, it's just like I was doing some practice and I noticed once you get wedges and dashes, it gets really weird.
Oh yeah, wedges and dashes with the diastereotopic and stuff like that with the rings.
Yeah.
Yeah, so let's talk about more complex examples here. Let's do talk about planar symmetry though. Let's say we have before we get to that, let's say we have something like this. Um, this one's gonna be a little bit trickier one. How many unique sets of hydrogen peaks would you do you see here?
For this one, I see, so those are the same, so that's 1, 2, 3, 4, 5, 6, 7, 8.
Mhm. 1, 2, 3, 4, 5, 6, 7. Yeah, 8.
Right.
Um, so these is one, this is one, this is another one, this is another one, another one, another one, another one, another one. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, you got it. So you know the planar symmetry rule already because this right here is a single bond which can do free rotation, making these three hydrogens the same as these three hydrogens right here. So that's good. And you know that these six are the same, and then these four are the same as well. So that's good. Nice. Okay. 8 unique sets of hydrogens. Okay. So now let's move on to rings. So let's say we have this ring right here, and then we have a wedge isopropyl, um, and then a dashed ethyl group right here. Okay. Now, how many unique sets of hydrogens would you expect for this one right here? This
This one,
one's a little bit trickier.
yeah, yeah. I was gonna say this one's a little trickier.
Hmm.
I was at the ATC and I think like
Hmm.
I was like what I got from it was some hydrogens are sticking out, some are sticking in, and you have to kind of
Hmm.
like turn it sideways, cut it in half, and then pick a number. So for this one, those are the same. So that's one group, uh, two, and then three, or 3, 4, 5, 6, 7, 8, 9. Six.
Huh? 6, 7.
Yeah, I just heard that.
6, 7.
9. Wait, I was on 7, 8, 9, 10, 11, 12, 13. Wait, I'm doing this so wrong. I just remember like on the rings, you count them as double because some are sticking out and then some
Hmm.
are sticking in.
Hmm.
Yeah.
So how I would do this is I would draw it out because this carbon here will have one hydrogen sticking up as a wedge, one hydrogen sticking down as a dash, and then let's do the same for all of them. And this hydrogen here has to be a wedge because the ethyl is a dash. And the hydrogen on this carbon has to be a dash because the isopropyl is a wedge. Now, you know how the isopropyl here is facing up towards you, and the ethyl here is facing down away from you into the page?
Mm-hmm.
If you imagine this flat planar bond of the ring and you cut it in half in the plane, right? Let's focus on this carbon over here. This hydrogen here is going to be different than that hydrogen over there. And that's because this hydrogen over here is going to be closer to the isopropyl group compared to the ethyl group, right? Because that hydrogen is on the same side as the isopropyl group. It's
I
facing
have a question.
towards you. Yeah.
Uh, do you always go for which one's facing towards you? Like, is that the one you always count?
Oh no, no. If you look for this one here away from you, that one, that one is going to be closer to the ethyl group compared to the isopropyl group because this hydrogen here is going to be facing the same side as the ethyl group. So the first one I chose, I just chose randomly.
Okay.
Yep, you could choose the one going away from you if you want, which is going to be closer to the ethyl group, also
Okay.
facing away from you.
Does it matter?
So it doesn't matter because they're gonna be because they're different. They're gonna be different unique peaks, right? And you know how in the previous example we were able to like rotate these hydrogens around?
Yeah.
Can we rotate these hydrogens around if it's in a ring like this?
No.
No, right. These bonds here cannot do free rotation, so they're stuck here. And
Okay.
because they're stuck there, they're gonna be different chemical environments.
Okay.
Right, like this wedge hydrogen here is closer to this wedge isopropyl. This dash hydrogen here is closer to this dash ethyl. And because they're different, they're gonna be experience different chemical environments. They're gonna show up as different peaks on the H and the MR.
Okay.
Yep. Okay. So there's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 sets of hydrogens. Right. So do these ones make sense on why they're unique sets right here? These circled ones?
Um, I'm not sure where you like did the, oh, well, there is one coming up from it. Okay.
This one right
I
here?
get it, yeah.
Yeah. So this one here like has six on that set. One, two, three, four, five, six. And all six hydrogens here have the same chemical environment because this is a single bond that's outside of the ring. And because it's outside of the ring, it can do free rotation. And because it can do free rotation, the three hydrogens here and the three hydrogens here can rotate into each other's spots like that. They could orbit around.
Okay.
And that's why they're gonna experience the same chemical environment. Right. Okay. Nice. Any questions on that, Tanya?
No.
Okay, that's good. That's good. Okay. So, did you want to go over this vocab questions? Did you have any questions, like which part in particular you want us to go over specifically?
No, I kind of want to just go through all them in
Mm-hmm.
general.
Okay, okay. So, let's go for A. Increasing the strength of the magnet will increase, decrease, keep constant the energy difference between the parallel and anti-parallel nuclei, and increase, decrease, keep constant the chemical shift in ppm. Okay. Before we move on, I want to make sure I know the right answer before I give you it. So I'm gonna say um keep constant for both of them. Is that true?
No, it's increase.
Increase for
Yeah, increase for
this
the
one,
first.
first one, and keep constant for the second one.
Yeah.
Okay, okay. Increase the energy difference between parallel and anti-parallel nuclei. Yeah. So I'm not too comfortable with the conceptual stuff behind HNMR. I just know like how to read the graph and predict the molecule accurately. With these information like the D shielded range, the neighbors integration, with the unique sets of peaks. But like I don't really understand how why the peaks show up like this. But let me try to find a way how. Let's see. Increasing the strength of the magnet will increase the energy difference between parallel and anti-parallel nuclei. Energy between. Oh yeah, so another thing that I could show you is that you know how when we shine um HNMR light down to let's say a shielded hydrogen, um this hydrogen here is shielded by electrons because there's no electronegative atom or electron withdrawing group pulling the electrons away. Whereas if we shine the light through a D-shielded hydrogen, it's able to pick up that hydrogen easily. It's able to read that hydrogen more easily because it's not surrounded by electrons since the electronegative atom is pulling the electrons away. When we put it through HNMR, all the electrons are gonna go into like let's say the electrons are here, they're floating into like random different orientations, right? If we put a magnet through it, like magnet, all these electrons are gonna go parallel to the magnet. Right, so let's say these are the electrons right here, and the magnet is going in this direction right here, or like anti-parallel, right? Um, increase the energy difference between strength of the magnet. So the stronger the magnet, the stronger the energy difference between the parallel and anti-parallel nuclei will be. But I'm not too sure why. That's more conceptual thing.
Maybe I can try like explaining what I
Mhm.
think, and then you
Yeah.
can add on a little.
Yeah. What do you have on your notes? Did she explain it on her lecture?
In the this is for discussion, and then in the discussion, I do
Mm-hmm.
have notes on this. There's actually a picture
Mm-hmm.
my teacher showed us, which helped me understand, and I watched a YouTube video too. Let
Mm-hmm.
me
Yeah,
see.
and you could share your screen too if you have an iPad, and then you could like draw stuff and then explain it to me and see how it goes.
Okay, yeah.
Yeah, let's do that. And also, I wanna give you a head start for next week's material because like I want to go over like the peaks and everything, so then you know how to read it as well. Maybe we could try one problem. We could try one problem.
NMR gets really bad, huh?
It does. It does get really, really bad. People get really scared of it at the end, and also alcohol reactions and synthesis as well. Like it gets tough at the end for sure. Of one is in A and B.
Oh no.
It does. I know. I know.
Oh, I have to give it permission to share screen.
Oh, you do? Let me see.
No, no, I have to like leave the Zoom meeting and then join back.
Wait, how about now?
No, it's just like my computer issue. I'll
Oh, okay, okay.
rejoin.
Yeah, yeah, okay.
Okay, and then share screen. That's entire screen. Okay.
Mhm.
I have so many tabs open. And then I'll share that. Okay. Can you see my iPad?
Yeah, I can see your iPad.
Okay. So for like the first question, it was like this chart that helped me understand and
Whoa,
this
wait,
YouTube.
how did you do that? Because like you're using Notability, right? And then like usually like when I share my screen on my iPad Notability, people can annotate on Zoom, but this one I can annotate on Zoom.
Oh, is what I did was I shared the screen from my computer, and then from my iPad, I shared the screen to my computer.
Oh, wow. Oh, yeah, I see. Are you like screen sharing it from like airplaying it from your MacBook?
Yeah.
Oh,
Yes.
okay, okay, okay. Dang. Okay, that's good. That's good. Yep.
So, so here, like, you have to input an energy for the magnet,
Mm-hmm.
and so the radio wave, it's gonna go through it, and then it switches it because it's like magnets. Like you have to really put in force if you want the north side facing the north and the south side facing the south. And
Mm-hmm.
eventually that HV is light, right? That's gonna go away and it's gonna return back to what it was before.
Mm-hmm.
So I think the question was increase in energy.
Mm-hmm. Increased energy would increase the energy difference. Energy difference. Increasing the magnet would
Is
increase the energy difference.
um yeah, it was this quiz. So it was increase. Oh, I should probably move that. Okay. It was increase the energy. And then right here, anti-parallel, and then Q constant of the shift in ppm. I'm not sure about that one. I think you got that one though, because you said keep constant for that.
Yeah, keep constant the chemical shift in ppm. So I just know that because when you read H&MR graphs from the 0 to 12 ppm range, the hydrogens over there, depending on where they're nearby, like carbonyls or electronegative atoms or alkenes, alcohols, and stuff like that, they're always within a certain range, right? It's always within a certain range. It doesn't really like go above 12. It doesn't go like if you increase the magnet a lot, it won't go up to like 2000 or something like that. It'll stay like around 12 as the max. So that's why I knew it was keep constant no matter how you change the energy um
Okay.
of the magnet,
Like,
the strength
like it might go up or down the scale, but the scale itself won't change, right?
yeah, the scale itself won't change. Right, like the relative peaks around would always be the same. It would always keep constant.
Okay. And then for letter B,
Mhm.
all hydrogens and carbons atoms are NMR active. Um, why is that false?
Yeah, so that's false because when we do HNMR, it's one HNMR, right? And you know how one HNMR only has one electron? You know how when you in chemistry, like when you fill up orbitals, how many orbitals, I mean, how many electrons can one orbital hold?
For hydrogen?
For any orbital. at all. Like when you before you move on to the next orbital, like 1s, 2s, 2p,
Oh, two.
2 electrons, right? And you know how you fill in the electrons, like how you draw it, like parallel and anti-parallel. Those 2 electrons would be in different directions, right? One would be like let's say facing up, and one would be facing down,
Yeah,
right?
like
Um, so when we shine, yeah, like that, right, like that. When we shine the magnet through it, right? The unpaired electrons, the lone electrons, are gonna be the ones that are gonna be reactive to the magnet, right? Whereas the paired electrons, like the one that has 2 electrons, they're stable. They are not gonna react to the magnet at all, right? So if you have like two H, like an isotope where it has like more electrons than it usually has, or like an even number of electrons, like two H NMR, it won't work. For carbon NMR, it's 13 CNMR. If there's a carbon that is 14 CNMR, with one more electron with no unpaired electrons, then they can't do NMR spectrum at all because it won't react with the magnet. So only the carbons or hydrogens with at least one unpaired electron, so an odd number, right? Like one H NMR, 13 CNMR would do NMR.
mm,
Mhm. Yeah. Right. So not all hydrogen or carbon atoms because there's isotopes of hydrogens and carbons, and some of those isotopes will will have no unpaired electrons, right? Like
okay.
they'll have an even number of electrons, which will
Depends
pair
on
up
the nucleus.
on the around the nucleus. And the electron cloud, two HNMR will have 2 electrons, and those 2 electrons will fill up the first orbital, right? And then because there's no unpaired electrons, they're not gonna react with the magnet.
Okay.
Mhm.
Mm. And then for C, D shielded H atoms, oh, I think you've talked about this just now.
Yeah.
When they're D shielded, you said you gave this example that this um atom kind of like takes away the
Hmm.
electrons.
Hmm.
They will have larger partial charges. I agree with that. D
Hmm.
shielded H atoms will tend to be downfield.
Hmm.
Okay, downfield.
Downfield. Yeah.
Uh, you have the something here. I forgot. It was like TM something, and
Uh-huh.
then this way is downfield,
Hmm.
and
Yep,
I
yep.
and then that downfield is like it can read it better, right?
Yep, it could read it better there, downfield, because it's D shielded there. D shielded downfield. DD.
And then that should the answer is wrong here. It should be on the left.
It should be on the left. Yeah.
Yeah. Okay.
Mhm. Yeah.
Then atoms are sp2.
We can
Uh.
go over this one. I was gonna go over this one, but this is
Okay.
part two.
Oh, this is part two. Oh.
Wait, it should be. I'm not sure. I don't know what's part one, part two, but I didn't go over this one yet with
Past
you.
the part one
This is
quiz.
part one, quiz.
Yeah.
Yeah. Okay. Okay. So let me share my screen again.
Okay.
Yeah. To go over this.
I'm gonna unshare.
Okay. Oh shoot. Let me clear this.
Oh, stop share. I see it. Okay.
Okay. So 0 to 2 is the most shielded region because this hydrogen here is not near any electronegative atom, not any interesting group, right? So it's going to be surrounded by electrons. The H&MR magnet cannot pick up or read that hydrogen very easily. But this 2 to 3 range is the alpha region where these alpha hydrogens are going to be on the alpha carbon, which is the first carbon away from my pi bond, right? Which could be that, or it could be from a alpha carbon coming off of an alkyne, or it could be a terminal alkyne itself, right? Which is not alpha, but it could be a terminal alkyne hydrogen like that. Now 3 to 4 is going to be the more interesting one, where it's going to be electronegative atom, where the hydrogen is going to be right next to an electronegative atom like oxygen, nitrogen, or any halogen. Okay, so let's say we have this group, and then let's say this is X, where X could be oxygen, nitrogen, fluorine, chlorine, bromine, iodine, right? Any electronegative atom. The hydrogen is going to come off of the same atom as the carbon holding the halogen, or the electronegative atom. Okay. Now 4 to 6 is going to be the alkene region, right? So when you have any kind of alkene, the hydrogens coming off of the alkene directly is going to be between 4 to 6. So that's sp2 hydrogen right there. sp3 hydrogen is right here, right? sp3, sp2. So sp2 hydrogens are more d-shielded than sp3 hydrogens. Um, Now the difference between this hydrogen and this hydrogen right here is that this hydrogen here is coming directly off of an sp2 carbon and a double bonded carbon, whereas this hydrogen here is coming off of an alpha carbon, the first carbon away from an sp2 carbon, right? Now 6 to 9, right, is gonna be the aromatic hydrogens, or the hydrogens coming off of a benzene ring. So if you see a benzene ring like that, and you see hydrogens coming off of that, then that means that there's going to be uh, hydrogens in the 6 to 9 range in the HNMR. Um, if you see a range at around 10, right, that's going to be the aldehyde hydrogen, right? Hydrogen. If you see a peak around 12, that's going to be the carboxylic acid hydrogen. So the most de-shielded peak here is going to be the carboxylic acid around 12. There's another peak, right? Which is gonna, in the discussion manual, it says it's gonna be around 0.5 to 4 or 5, right? 0.5 to 4. And then those are gonna be the alcohol or amine hydrogens like NH2 or secondary amine with NH right there. Right. And you get to know by the integration, it'll tell you like how many hydrogens there are. And those peaks here are gonna be broad, right? And they're going to be broad because of something called H bonds. Like in the IR, the broad peak had H bonds, right? Where the hydrogens are bonded to fluorine, oxygen, or nitrogen. Every other peak in the HNMI would be sharp, but if you have an alcohol or amine with an H bond, it's going to be a broad peak, and usually between 3 to 4, but on the discussion manual, it would say like 0.5 to 4 or 0.5 to 5. Um, so that's the regions of where the hydrogens are going to be specifically for HNMR. That's the D-shielded part of HNMR. Um, Integration is going to be the smallest ratio, right? Smallest ratio. So what I mean by that is something like this. Um, if I were to give you, let's say, um, mm, 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 this symmetrical molecule over here, these blue hydrogens over here are going to be the exact same as these blue hydrogens over here. So this one blue peak is going to have 3, 6, 9, 12. 12 hydrogens in that one set. These pink hydrogens over here are going to be in another set. And then these green hydrogens here are going to be the third set. Right? 3, 6, 9, 12, 2, 4, 6, 8. So instead of having the integration as 12 blue hydrogens, 2, 4, 6, 8, 8 pink hydrogens, and 2 green hydrogens on the HNMR, they're gonna simplify this down into 6, 4, and 1. right? Just divide everything by the smallest whole number to get the smallest ratio between the unique sets of hydrogens. So on the HNMR, if you're given the HNMR of this molecule here, they won't give you this ratio on the integration. They'll give you this ratio over here for the integration. But you'll know that this is going to be the specific structure because they will give you the chemical formula, which will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like C10H, like 22, right? And then you know that if you're given 6, 4, and 1 as the integration, if you add that up, that's going to be 11 hydrogens, right? 11 hydrogens, which does not match up with the chemical formula of 22 hydrogens. So you know that this is a simplified ratio of an integration of the HNMR, right? Which is a times 2 to get the actual number of hydrogens in the chemical formula. Okay, it'll be more clear as we go over like actual practice problems and the discussion manual, but this is just conceptual stuff, right, for integration. Now the n+1 rule, which is neighbors. Let's say we start off with a simple molecule like uh, let's go back to this molecule right here with bromine, right? This is one unique set of hydrogens, which is the blue hydrogens. This is another set of hydrogens. This is another set of hydrogens, and this is another set of hydrogens right here. Okay, and we can actually predict like where they're gonna be on the HMR, but I'm gonna reduce this down to like 0 to let's say 5. Okay, 0 yeah, 0 to 5, because the most d-shielded range is gonna be can you tell me what color here is gonna be the most d-shielded peak based on this region that we this chart we talked about right here? Like and you
And
could also think about it like in terms of the concept that we talked about. Which hydrogen is going to be the most d-shielded here?
the purple one, because it's closest to the electronegative
Uh-huh.
thing.
Yeah, the purple one because it's the closest to the most electronegative atom. That is gonna pull on the hydrogen's electrons, making it the most d-shielded. So it's gonna be on the most left side. And we said earlier that that hydrogen next to the electronegative atom is gonna be between 0 to I mean 3 to 4. Oh, wait, it could be 5 as well. So let's just say this is 1, 2, 3, 4, something like that. Okay. And I said that peak right there, the purple peak, is going to be between here, like 3 to 4, around that range. Now, let's talk about neighbors, right? Which is going to be 3 bonds away from the hydrogen. So if we look at this purple hydrogen over here, and we count 3 away, this is 1, this is 2, this is 3. That counts as a neighbor. 1, 2, 3 counts as a neighbor. 1, 2, 3 counts as a neighbor. 1, 2, 3 counts as a neighbor. 1, 2, 3. This is a carbon, not a hydrogen. That does not count as a neighbor. 1, 2, 3. That's a carbon. Does not count as a neighbor. These hydrogens here are way too far away to become neighbors of the purple hydrogen because those hydrogens are 4 bonds away, right? So it cannot be that purple hydrogen's neighbor. So this purple hydrogen here will have 1, 2, 3, 4 neighbors. Any questions on that, Tanya, on how I got 4 neighbors for that purple hydrogen?
No.
Okay, so on the HNMR, it's going to show up as n+1. 4 plus 1 is 5, so that's going to be a quintet, right? Like that, 1H. And I made it small because it's only one hydrogen. The height of the peak is going to represent the integration, which is how many hydrogens are in the peak. And because it's only one hydrogen, it's going to be the shortest peak compared to the other peaks except the green, okay? It's 3 to 4, right? Because it's right next to the bromine. It has 5 sub peaks, 1, 2, 3, 4, 5, because it has 4 neighbors. So if you're given an HNMR, know that neighbors will equal sub peaks minus 1, right? So this purple hydrogen here peak will have, because it has 1, 2, 3, 4, 5, 5 sub peaks, 5 minus 1 is 4 neighbors, right? And then we see that here, that purple hydrogen has 4 neighbors, 1, 2, 3, 4. Okay. Can you tell me how many neighbors the pink hydrogen will have?
One.
One. Yes. Uh-huh. One neighbor. That's good. Um, how about the the green hydrogen?
7.
One, two, three, four, five, six, seven. Nice. How about the blue hydrogen?
1.
One. Right. Correct. And I'm gonna draw that here. Um, pink, green, and purple are alkane, so they're gonna be between 0 to 2. Pink and green should be more D-shielded than blue because they're closer to the bromine. So I'll start with green. Uh, 7. So that's gonna be 1, 2, 3, 4, 5, 6, 7. One H. Pink has 3, so with one neighbor, so it's gonna be doublet like that. 3H. And then blue will have one neighbor. That's gonna be doublet as well, but it's gonna be 6 like that. Do you understand the reason why these hydrogen peaks are in different locations and why they have different sub peaks and why they have different heights?
So the height is because of the amount, right?
Yeah, right. The height is because of the amount, which is will be known as integration.
So the purple and the green one, they're like supposed to be the same height because they're both 1H or no?
Yeah, yeah, they're supposed to be the same height. Yeah,
Okay, okay. Okay,
yeah.
yeah, that makes sense. Thank you.
Yep. How about the sub peaks? What do the sub peaks represent?
Um, like how many peaks there are within one peak?
Oh, so it's not gonna be how many peaks there are within one peak. It's gonna be how many neighbors each peak has.
Yeah, so it's n plus 1.
N plus one, right? How many neighbors, right? How about the location of the peaks, like the shielded versus shielded peaks?
The location, I know you drew the chart, but the way I kind of see it now, since I haven't got there yet,
Hmm.
is it's further away from the bromine, the electronegative atom.
Yeah. Like blue is the furthest away from the electronegative atom, so it's gonna be the most shielded, right? It's not gonna be de-shielded by the bromine as much.
Yay.
Nice, nice. And this right here, like what you're gonna have to do is that you're gonna be given a chemical formula, right? Like whatever it is, like CHO or N something. You're gonna be given a random HNMR, and you're gonna have to predict this molecule from scratch. Like they're not gonna give you this. You're gonna have to predict that from scratch.
Whoa.
Right? But there's some tricks to it. Like an isopropyl group, right, of a molecule will always have this pair of peaks right here, where you have one short hydrogen peak with a lot of neighbors and 6 hydrogens with a doublet like that. Because that represents like one hydrogen with a lot of neighbors, this one right here, and 6 hydrogens with only one neighbor, which is that one right there. Right? So when you have an isopropyl group, you know that by if you see this pair of peaks right here together.
Oh.
And we see that here.
So
This is
it's
the
like with like practice, you like kind of figure these things out.
yeah, with practice you will notice patterns and you'll get faster with it. Right. And there's ways to do it as well. And I could go through a lot of practice ones with you for office hours or our next session. But another pattern I could give you right now is tert-butyl group. So let's say we have a tert-butyl group right here, right? Um, how many hydrogens are going to be unique in a tert-butyl group?
Um, there's going to be 3, 6, 9, 9.
9, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many neighbors will this 9 hydrogens have?
Uh, it doesn't have any neighbors.
Mm-hmm. It will not have any neighbors. So it's going to be 0 plus 1, which is 1, a singlet.
Okay.
So it's gonna be one big long singlet like that, 9 hydrogens. So if you see a really big long singlet like that with 9 hydrogens, you know that your molecule, your other molecule will have a tert-butyl group.
Um, oh yeah, that makes sense.
Hmm. Because if you go like any, it doesn't matter. You could choose any hydrogen. Let's say we choose this hydrogen here. If we go 3 bonds away, 1, 2, 3, 1, 2, 3, it's gonna hit a carbon. It's not gonna hit a hydrogen. It's gonna hit some carbon atom or oxygen or nitrogen or fluorine or chlorine, bromine, a non-hydrogen atom.
Oh,
Does that make sense? Any questions on that, Tanya? Hello, hello. Oh wait, I think you're muted.
Oh, is this working now?
Oh yeah, yeah. Oh, it's working now. Okay, okay. Any questions on this, Tanya? Oh, shoot, I think you're muted again, Tanya.
No.
Okay, okay. Let's go back to this right here. Okay. So this one here should be to the left, not the right. Okay. Answer D.
Atoms are sp2. So I know when I like see something like that, I think about like a carbon.
Mm-hmm.
And I know that if it's sp2, it will have uh it will have like a double bond,
Mm-hmm.
right?
Yep.
Um and it has larger, smaller, about the same chemical
Oh yeah, yeah.
okay, sorry. Chemical shifts
Uh-huh.
as atoms are sp2. Yeah, I would draw them out like that also.
Mm-hmm. Right.
I think like double bond would make it the double bond would yeah, it would make it larger because like I was at actually the AATC talking about this with a tutor,
Uh-huh.
and honestly I didn't understand the explanation. It's just like I remember double bond means that there's gonna be more of a pull going towards it.
Mm-hmm. Yeah. And also we could look at this chart right here where you know
Yeah.
how we have a double bond right here where the hydrogen is coming off of the double bond. It's between 4 to 6. Whereas this carbon here is on an sp3 carbon, 0 to 2. So that's how we know that it's gonna be more deshielded. And the reason why is because let's think about it conceptually. If this hydrogen is more deshielded, that means there's less electrons around this hydrogen. Let's say there's like 3 hydrogens around that hydrogen right there. Or 4. Right? And then the hydrogen over here is gonna have like 10 hydrogens around it or something like that. It's gonna be more shielded. And the reason why is because when you learn about alkenes in 118b, at the beginning of 118b, you're gonna learn that you technically kind of already learned it in 118a, but how many electrons does this bond represent right here? And
Two.
then we're gonna focus on this hydrogen right here. 2, yes. Let's say we could do resonance like that, where the 2 electrons are gonna go onto this carbon right here. We're gonna
Oh
get
no,
this
resonance.
resonance structure right here. Yeah, how did you do on that quiz, that resonance quiz?
Oh, I don't remember. I think I
Uh-huh.
did like okay, it was one of my better quizzes. And it's
Yeah.
just like I don't want to remember it.
Yeah, yeah,
It
yeah,
was
yeah.
kind of
Wait, I,
yeah.
wa- I, want, I want to test you something. I want to test you on something. What
No.
is the hybridization of this right here? This nitrogen atom.
Oh. Um, you want me to do the resonance of it?
No, 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 no. Can you do resonance here?
Um, no, because like it can't make any
Yeah,
because
yeah.
nitrogen only has three.
Cannot do any resonance here. So what would the hybridization be here?
Oh, so it's like sp3 because you include the lone pair.
Yeah, sp3. 1, 2, 3, 4. Now, how about this right here? This nitrogen atom right here.
Oh, this is like the trick where they like put like the ketone next to it and then it's supposed to like trick you and then like something about electronegativity and I was like, okay, it's sp2.
sp2, yeah. And that's because it looks
Oh,
sp3, right? With 1, 2,
yeah,
3,
it does. Yeah, it does.
right? But you got sp2 because of resonance. If we push the
Oh,
lone pair down and do resonance like this, we're gonna get this resonance structure right here.
Yeah, I noticed that like in all structures, the oxygen like always ends up losing its like the ketone always ends up losing a bond and
Uh-huh.
it becomes negative.
Yeah, yeah, that's gonna be very common. That's good that you noticed that. It's gonna be very common for reactions and mechanisms.
Yay. I'm doing good.
Yes, that's good. If you see three here, and that's gonna be not sp3 but sp2. And we prefer sp2 because if we have sp2 atom, that means there's one p orbital, and we want that p orbital to do resonance because resonance will stabilize the molecule more. It will make the
Mhm.
molecule more happy with resonance, more delocalization. The electrons will have more room to move around to breathe in. Okay. Uh now let's go to here, back here. So this one here, do you understand why atoms that are sp2 have a larger chemical shift than atoms that are sp3 hybridized?
Yeah,
Oh wait,
you were
I didn't
talking
finish the
about
explanation yet. Oops, oopsie. Uh,
residence.
yeah, resonance, right?
Okay.
And um, you know how when we did this resonance over here, and we'll
Mhm.
focus on this hydrogen right here, that's on the sp2 atom.
Yeah.
This carbon here is a carbocation. A cation is something that's positively charged, and a carbon with that positive charge is going to be called a carbocation. Carbocation, right? This carbocation here is very sad, very angry now. Okay, because it's positively charged. It's unstable. Like it's unstable with that formal charge, and because it's very unstable with a positive charge, it's missing electrons. Like it has a void of electrons, so it's gonna pull or withdraw electrons from the hydrogen towards that carbon right there, making this hydrogen more
Mm.
de-shielded.
Okay. Yeah, that makes sense.
Yeah, yeah.
Okay, so because of resonance, the hydrogen it becomes more deshielded. So
Yep.
like it gets seen. Okay.
Yeah, yeah. And there's something about magnets as well. But you'll learn about that in 118B. 118B.
Yeah.
But then that's good enough for one explanation with resonance. And I just would segue here to give you a tricky problem for resonance. But you got it. You got it though. That's good. Okay. Let's see. Do you think you would have gotten it if I gave you this first without this?
Um, I don't think so.
Shoot. Okay, okay, okay.
Uh,
Let's do E.
I actually printed out the scale on my note card.
Hmm.
I see that like most of the numbers are from 0.7 to 12.
Yeah,
So I
yeah.
would just say no.
Yeah, it's gonna be 0 to 12. Right. 0 to 200, that's gonna be CNMR. And I don't think you've learned about that yet.
No, we only done HNMR.
Yeah. Mm-hmm.
And then integration shows, oh, I don't even think we learned about integration, but I think I can answer this. Integration shows the exact ratio of smallest total number of the, um, is it smallest whole number ratio?
Yeah, smallest whole number ratio. Because remember when we went over this molecule in particular right here? Um, hello. Oh, this one right here. It was like 1282, but then we simplified it to the smallest whole number ratio. It's gonna be like that. Smallest whole number ratio. Yep. Mm-hmm. Okay.
Oh,
Next.
wow. I actually couldn't answer these questions before. Now I can.
Yes, let's go. You're learning.
And then OH and NH show up in broadened peaks in the NMR and will tend to, oh, this one I actually don't know. I
Yeah,
know,
before.
I remember from IR, I think they were together, so I would have put true for that, but I don't know about NMR.
Yeah, so NMR, OH and NH, what do they have? What kind of specific bond do they have?
Um, single bond.
Uh-huh. Single bond between a hydrogen and one of these atoms, FON, which is
Mhm.
called a hydrogen bond. And hydrogen bonds in IR and HNMR will show up as a broad peak,
Oh,
right?
so I think for this quiz, I might need to actually go over the types of the chart.
Mm-hmm. The chart, yeah. But for
Yeah.
HNMR, it's only one broad peak, which is alcohol and amine with hydrogen. Right. Every other peak in the HNMR will be sharp.
Okay. Okay. Does the discussion manual have it?
Next week I want to go over practice NMR problem with you, like from scratch with the chemical formula and HNMR problem, and then we predict through it. And there's general guidelines, like different people do it, approach it differently. But I'll show you mine, and then I'll have you practice, and then you talk through your thought process of another problem.
Okay, okay, for sure. I appreciate it. Thank you.
Yep, of course, of course. And then you just gave me a Kahoot idea for the next first Kahoot, the NMR.
Yeah, yeah, NMR is a tough topic.
Yeah. Okay. Any questions, Tanya? Other questions?
Do you think you can send me the picture of the chart you drew?
Oh yeah, yeah. I'll send you the notes of this, or you can screenshot this right here.
Okay,
Like this.
all right. Thank you.
Of course. Okay. As a homework problem, I want you to tell me the unique number of unique peaks, number of unique peaks of hydrogens. And then from there, I want you to tell me the number of subpeaks of each peak. And oh shoot, this might be too much. Huh. Okay, like that. I just want to be like comprehensive as possible. Tell me integration of each peak, and then also the approximate chemical shift, or de-shielded versus shielded chemical ppm, chemical shift of each peak, and that will help you in part two a lot. Okay, you can use that chart. And another thing is that things with hydrogen bonds, like let's say alcohol, right? And I'm gonna draw this bond out explicitly. If we focus on this alcohol hydrogen bond right here, and you count three away, 1, 2, 3, this hydrogen here is not a neighbor of alcohol hydrogen because of the H bond, right? So any bond that is bonded to an electronegative or heteroatom, right? Like this is bonded to a heteroatom, which is a non-carbon atom. They cannot have neighbors. Heteroatom cannot have neighbors. Okay. Okay. So that will help you there. Okay. All those things and the class was about to start second. I cannot. Okay. Yeah. That's good. Okay. I will thank you, Tanya, and I will see you maybe this Saturday and next week for our next session. Okay. That's good. That's good. You're in an empty classroom. Yep. Okay, okay. That's good. That's good. Okay. Bye bye.